We've just met three different kinds of row operation. In this video, we're going to see how the effect of a row operation is the same as multiplying on the left by a certain matrix called an elementary matrix. Here's the definition. An elementary matrix is one that you can get by doing a single row operation to an identity matrix. For example, first of all, the elementary matrix 0, 1, 1, 0 is the one that you get by doing the row operation which swaps row 1 and row 2 to the identity matrix I2. The next elementary matrix is the one that you get by doing the row operation which sends row 1 to row 1 plus 2 times the row 2 to the 3 by 3 identity matrix. If you want to convince yourself of this, here is the 3 by 3 identity matrix. And you can see if I add 2 times row 2 to row 1, that really is the matrix that I get. Finally, to see the effect of the third type of row operation, here is the elementary matrix which arises from doing the row operation which multiplies row 1 by minus 1 to the 2 by 2 identity matrix. The important theorem for this video is the following. It says if you have a row operation R and an m by n matrix A, then doing R to A is the same as left multiplying A by what you get by applying R to the m by m identity matrix. In other words, the effect of doing the row operation R is the same as the effect of left multiplying by the elementary matrix corresponding to the row operation R. I'm not going to give a proof of this theorem in the video. If you'd like to see a proof for all three different kinds of row operation, you can look that up in the online notes. What I will do is show an example, in fact a couple of examples. So let's look first at the 2 by 2 case, so m equals n equals 2, and we will take R to be the row operation which swaps row 1 and row 2. We'll let A be a general 2 by 2 matrix, A, B, C, D. We also need to know what the elementary matrix corresponding to R is. So that's R applied to the 2 by 2 identity, and actually we've already seen that what you get when you do this is 0, 1, 1, 0. What the theorem claims is that doing R to A should be the same as left multiplying A by R of I2. So let's work both of those things out. R of A, well, to get R of A, I've got to swap rows 1 and 2, so that should be C, D, A, B. Now let's do the left multiplication of R of I2 times A, and you can see what happens here. To get the 1, 1 entry, I do 0 times A plus 1 times C. To get the 1, 2 entry, I do 0 times B plus 1 times D. And similarly, I'll get an AB down here. And we really do have that R of A and R of I2 multiplied by A are the same. Let's try a different one now. So we'll try R being the row operation which sends R2 to R2 plus 2R1. Again, I'm going to take A to be the general 2 by 2 matrix, A, B, C, D, and I need to know what the elementary matrix corresponding to this row operation is. That's R applied to the 2 by 2 identity. So I have to take the 2 by 2 identity and add 2 times row 1 to row 2. So row 1 will just be the same as it always is, and then I'll have a 2 and a 1, like this. Now let's check that agrees with that when we multiply on the left by this matrix, that agrees with R of A. So we should work out R of A. I have to add 2 times R1 to R2, so I'll get R1 unchanged, and R2, row 2, will be C plus 2A, and then D plus 2B. So let's now work out R of I2 times A. 1, 0, 2, 1 times A, B, C, D is, well, you can see that the first row is going to be the same as the first row of A, because I'll get 1 times A plus 0 times C in position 1, 1, 1 times B plus 0 times D in position 1, 2, and next in position 2, 1, I'll get 2A plus 1C, and in position 2, 2, I'll have 2B plus D. So these two things are equal, and that illustrates the theorem in this particular special case. As I said before, if you'd like to see the general proof for all matrices in all 3 types of row ops, you can see that in the online notes for 0007. A useful corollary of this result is that any elementary matrix is invertible. Remember, an elementary matrix is one that you get by applying a single row operation to an identity matrix. Here's the proof. So we take any row op R, and we remember that in the previous video we saw that every row op has an inverse. So we'll let S be the inverse row op to R. A row op is of course short for row operation here. We need to show that the elementary matrix R of IN is invertible, and the way that we're going to do that is by showing that its inverse is S of IN. So we have to show that R of n times S of IN and S of n IN times R of IN is equal to the identity. So let's write this down. That's what it means for S of IN to be the inverse of R of IN. So that's what we need to check. Now, on the previous slide we proved a theorem which said that for any matrix A, R of A was the same as R of IN times A. That was our theorem from the last slide. So if we take A to be S of IN, then R of IN times S of IN will be the same as R of S of IN. So this is playing the role of A. But of course R and S were supposed to be inverses of one another, so doing S then doing R should be the same as doing nothing. That means what we've got there is really the identity matrix, so R of IN times S of IN is equal to the identity matrix. That proves half of what we need to prove. But if we think about S of IN times R of IN, well, we could use the same result only with S in place of R and with this as our matrix A. And that would tell us that S of IN times R of IN was S of R of IN. And since S and R are inverses, this would just be the identity matrix again. That completes our proof, so we know that every elementary matrix is invertible, and we even know what its inverse is.